Okay, so so I'm starting this session by introducing myself. I am Moina Ghoshal, PMRF and a research scholar at Indian Institute of Science Education and Research, Kolkata. And I have been assigned as the TA for this course, which is entitled as Fundamentals of Spectroscopy, which was instructed by Professor Sayan Bakshi and Professor Anirban Hajra. And this is related to assignment questions related to week number 8, where I am going to solve some questions regarding the lectures that was actually finalized for this week number 8 as the content. And so I will solve some questions which will give you some idea about how to solve them. Okay. So you know this that in the previous classes I have discussed about the basic forms of spectroscopy, and also there was a discussion on rotational and vibrational spectroscopy. So I am going to the previous days queries that about previous week assignment. This was the topics that was discussed. Okay, just a minute to check. Yes. Okay. So this was actually discussed in the previous live session where there was a discussion on PQR branch. Okay. So first of all, whenever we have discussed rotational in spectroscopy, then we have moved to vibrational spectroscopy. And in vibrational spectroscopy, after the vibrational spectroscopy, we have moved to roto vibrational spectroscopy, low vibrational spectroscopy. There, three different kinds of bands appeared. One is P branch, another is Q branch, another is and P branch and R branch are mainly there. So after this was actually observed that in P branch, these rotational lines, it was shown that it gets separated from each other, whereas in case of R branch, the lines comes closer. Okay, so this was actually shown that the main cause is that whenever we had derived earlier, we have thought that the B values for this ground vibrational level and excited vibrational level is same, but that is not the case. Okay, so that was not the case. Actually, it was shown that B depends. Yeah. So who have joined now? So can you clearly hear me? Can you hear me clearly? Priyadarshini, can you hear me clearly? Okay, so yeah, so there was the discussion on anharmonicity and how B depends on vibrational quantum numbers. Okay, it was shown that in the earlier case, it was shown that these two are, I mean, the lines in the P branch and Q branch, R branch are equal. Okay, That is, they are separated by each other by the same value. But it was in practice, it was observed that pre-branch lines are get separated from each other, whereas for R branch the lines are coming closer to each other, and it was shown that the B depends upon V, which is, that means, by this expression. Okay, so using this expression, as V increases, the B will decrease. Okay, so for different vibrational levels, B will be different, and this, by this reason it was explained that why this is so, because for that is, in P branch lines are separated from each other, but in QR branch they are coming closer to each other. And then these values of B0 and B1, it was determined by choosing appropriate lines in the P and R branch. Okay, so appropriate lines in the P and R branch for different J values, you can assure that what should be the B value. Then there was a discussion on this transition corresponding to delta J equal to 0, and there was appearance of this Q branch, which was not present earlier. In the earlier cases, there was some discussion of P branch and R branch, but here, if delta J is equals to 0 condition is satisfied, then you can observe also Q branch. Next, the normal modes of vibration was observed for an atomic molecule, and it was observed that for 3n minus 5 will be there for linear molecules, and 3n minus 6 vibrations will be there for non-linear molecules. And also for water, it was shown that the 3 bands will be there because water is a non-linear molecule. So if you put n equals to 3, and here this, you have written this formula for non-linear molecules, 3n minus 6. So 3 into 3 minus 6, that will give you 3. That means here are 3 bands will be there, and it is also observed for water as 3 bands. But for carbon dioxide, only 2 bands are observed because the 2 bending modes, they come in the exactly same positions. Okay, and it was discussed. And then symmetry elements of a molecule in the group theory that was observed. That is Cn, sigma b, E, etc. Cn is the axis of rotation with respect to if you rotate. Cn means, if you rotate this by angle of 360 by n, you will get the identical conformation. You have also learned it in the stereochemistry. Also, there is sigma v, that means vertical plane which will bisect this molecule. Okay, and E is the identity. Every molecule has this identity element. And then this was discussed about the symmetry element that is present in water molecule. Okay, water molecule has this point group of C2V, and C2V point group contains C2 sigma 2 sigma V axis. So sorry, 2 sigma V elements. Okay, so one E, one C2, and 2 different sigma V. And then from this vibrational modes was calculated that which corresponds to which one. Okay, and then the symmetry of wave functions of any vibrational levels were determined, and what should be the intensity of transition, it was also talked about. We have also discussed about that. And then the selection rule for rotational vibrational spectroscopy of polyatomic molecules, it was done in terms of symmetry. Okay, it was shown that totally symmetric configuration, which is also known as in the terms of group theory as A1, totally symmetric configuration, it will give you the highly intense line. Okay, otherwise it is allowed only if this is A1. If the multiplication is not giving the symmetry A1, it is forbidden. Then parallel and perpendicular mode discussion was done. This was about the direction of this dipole moment with the principal axis. And then it was observed that in case of perpendicular mode, PQ band profile is observed. Okay, that means, and Q band is also observed mainly for bending modes of HCN and CO2. Next, skeletal vibration and group vibration of polyatomic molecules are discussed, which is mainly useful as an application tool for IR spectroscopy, where skeletal vibration occurs within mainly what was the region? It is the region was from 700 to 14,000 inverse. So in within this region, this is 14,000. Okay? So 700 to 14,000 centimeter inverse, and the group vibration for polyatomic molecules. What should be the group vibration? That means When one group is vibrating, this is devoid of any other environment that is present there. And then this was discussed that how this is present in an IR spectra. One IR spectra was shown, and from that, what is the skeletal vibration region, what is the group vibration region, it was also discussed, and for which functional group group vibration will be where, this was also discussed. Okay. And next, the total potential energy was written as the sum of 3n minus 6 different one-dimensional potential energies. This was applicable for non-linear molecule because you know for non-linear molecule there will be 3n minus 6 number of vibrations. Okay, so you can write this potential energy as a function of 3n minus 6 different one-dimensional potential energy. And it was also mentioned that this is applicable only for normal mode coordinates. And the same thing happened for the Hamiltonian of the system. That is, the total Hamiltonian of the system was also expressed the sum of individual 1D harmonic oscillators. Okay, but the frequency was different. And also, finally, in normal mode vibration, all the atoms move together such that center of mass is not changed. Center of mass, suppose it was shown that suppose in case of water molecule, two hydrogen molecules are going there. Okay, so oxygen molecule will move itself in such a way that the center of mass is remain fixed. Okay, so this is actually happens in case of normal vibration. So this was the previous week's discussion that I have taken session on, and this was also discussed, and several questions were discussed about this P branch, Q branch, and also P branch, Q branch, R branch, and also parallel, perpendicular, mode, and skeletal group vibration also there. Yeah. Okay. So this was the previous week's discussion. I have given you a small recap. Now I'm moving to today's discussion, which is on another spectroscopic technique that you will understand or you will learn. Okay. So earlier, this was a discussion on spectroscopy, where how spectroscopy was developed, how why do you need spectroscopy, what is the advantage and disadvantage of the spectroscopy, and how different forms of spectroscopy was shown that in which region of this electromagnetic spectrum your spectroscopic transition lies. Okay, so all transitions doesn't lie in the same region. Some transitions lie in the microwave, some in the IR range, some in the visible range, etc. Okay. Upon based on that, two different spectroscopic techniques were discussed. One is rotational spectroscopy, for which you need microwave radiation. Another is IR spectroscopy or vibrational spectroscopy, for which you need IR radiation or infrared radiation. And then there was a merge of this rotational and vibrational thing, which gives you true vibrational spectroscopy. So this was all the topics that we have discussed so far. Now we are going to learn something new. Okay. So do you know who he is? Do you know him? Do you know him? Okay, so he needs no introduction. Actually, he's a legend. So he is C.V. Raman. Okay, C.V. Raman. So today we are going to learn the new spectroscopic technique, which is known as Raman spectroscopy. Okay, so he has won the Nobel Prize in Physics in 1930 when he has discovered this kind of thing, which is what is known as scattering of light. So he has won the Nobel Prize for scattering of light. He has discovered that. How he has discovered? The exact date was 20th. Okay, so which is celebrated as the National Science Day, as Professor Sayan Bakshi has said. And this scattering of light, actually, he has observed this scattering of light by naked eye. Okay, this was a trivial experiment. and what I say, I don't know. So extremely new field which people are working in nowadays all over the world. Okay, so the and he also named this spectroscopy or this scattering of light is known as after his name as Raman spectroscopy. Okay, so Raman spectroscopy was discovered by Professor C.B. Raman, and he has won Nobel Prize in the due to this discovery in 1930. So now I'm coming to this lecture material. What was taught actually? So actually, it was shown that Raman spectroscopy is nothing but a scattering of light. Okay, and two types of scattering was discovered. Whenever light falls on a matter, two the different things happen. Some part of the light is absorbed, some is transmitted, and the other is scattered. Okay, the scattering is observed, which is directly proportional. This intensity is proportional to lambda to the power 1 by lambda to the power 4, or here it is written as lambda to the power minus 4. And also, and most of and whenever this light falls, the most of like some light which is scattering, they will have the different intensity, but the energy of the light will be same. But round have observed that although we are getting they have got the same energy scattered light, also they have got other scattered lights which have different energy or different wavelength. Okay, so sorry, he has named that as Raman scattering. Okay, so this was actually came into his mind as it was earlier discussed that what is Compton effect. Okay, so from this idea he has used this for molecules, and he have with the naked eye he has shown that some scattering is happening. Okay, and to give some light into this, he has put what should be the equation that, and he has said that this depends upon induced dipole moment. Okay, so what is induced dipole moment? Whenever there is when in the molecule the electrons are arranged properly. Okay, so when some electric field is applied, so the electron density will change. Okay, so electron will redistribute itself, and thus they will create a dipole. So this dipole is called induced dipole. Okay, so this induced dipole is related to mu induced related to E. Okay, so from this, if you make it equal, this there should be something alpha to E. Okay, so this alpha which is called polarizability. Okay, so alpha is called polarizability. Okay, then there was a discussion on the formula of mu induced and how it is dependent on time. Okay, so mu induced was defined as mu induced I have the expression with me for mu induced is alpha 0 is 0 cos 2 pi mu 0 t plus okay, for writing difference in term first, so d alpha by dq at q is equals to or equilibrium, so d alpha by dq, so d alpha by dq into which is a q0 e0 upon 2 is e0 upon 2 into cos 2 pi nu 0 minus nu m into t plus cos 2 pi mu 0 plus mu m 50. So this will be the expression. Okay. So Professor Sandberg has derived this expression. I am just taking it from this expression. So you can see here that how it is depend upon time, and also you can see three different frequencies could be there. Okay. So either this will be equals to mu 0, and also this mu 0 minus mu m, another will be mu 0 plus mu m. So three different kinds of things will be there. Correspondingly, we can say that your Rayleigh line will be there. One will be Stokes line, another will be anti-Stokes line. So this is called Rayleigh scattering. That means which have the same wavelength, the same energy as the incident radiation. This is called Raman Stokes scattering, and this is called Raman anti-Stokes scattering. Okay. So this was the expression which was used to see how this alpha will depend upon Q. So first and foremost condition for the Raman scattering is that you need, yeah, first and foremost condition is that your dAgu by dQ should be not equals to 0. So if this is equals to 0, your all game will be vanished because this term will be 0. So your polarizability will change with the displacement of the atom. So we'll come later to a question where this concept will be needed. Okay. Next, in lecture number 38, there was a discussion on Rayleigh Stokes and anti-Stokes scattering in the light of time-dependent perturbation theory, and there was a concept of virtual state. Okay. So this is completely different from previous discussions of IR and rotational spectroscopy, where you have considered something higher in energy as excited state. Okay, but here in case of Raman spectroscopy, there is nothing such like excited state. This is a very temporary state, virtual state, which is gone. So if I am going to draw, yeah. So this is my initial state and this is my final state. So it is coming from here. So this is my initial state. This is my final state. Okay, so coming to here and it is coming here. So this is Rayleigh scattering. Okay, whatever be the initial state, it will be the final state. But in case of Raman scattering, suppose this is my initial state, this is my final state. So it is coming over here, but it is coming to this final state. So this is called Stokes scattering, Raman Stokes line. And the same phenomena is happening if it is happening from this is the initial state and this is the final state, and so it is happening from here, it is coming to over here. Okay, so this is called anti-Stokes line or anti-Stokes scattering. Okay, so three different kinds of phenomena you can observe in case of Raman spectroscopy. One is Rayleigh scattering, another is Stokes scattering, another is anti-Stokes scattering. And now you know what should be the intensity of the Stokes and anti-Stokes line. And this is very much crucial because there will be a question, very logical question will be there about this Stokes and anti-Stokes line. Okay, so you know for the intensity of Stokes and anti-Stokes, what on what factor this intensity depends? This intensity actually depends on population. Okay, as much as you have population, the intensity will be that much. Okay, so in the initial state, you know, the room temperature, the ground levels are much more populated. That means, and since Stokes lines appears from the ground state, you can see here. Yeah. So you can see here for Stokes case, it is coming. It is the transition is happening from the very ground level. Okay, but for the case of anti-Stokes line, the transition is coming from the excited level or which is higher in energy state. Okay, so and since I have said according to Boltzmann distribution, the ground vibrational state or ground states will be much more populated in at room temperature. So the Stokes line intensity will be, if you see any kind of spectra, Raman spectra, you can see there that the Stokes lines will have much more intensity compared to anti-Stokes lines. Okay, and then there was a difference between the probability of transition for other spectroscopic transition and Raman spectroscopy. This was given in terms of transition moment integral. So for other spectroscopic technique, what you used to write is like probability is written as f mu I. This part is squared. That is transition moment integral square. But for for Raman, for case of Raman, so for Raman, it was observed that this turn probability is defined as f mu v v mu I. This whole square. So there was an involvement of this virtual state in this expression of transition moment integral or in the probability. Okay, so it is somewhat different from normal spectroscopic transitions. Okay. Next, in the next lecture, there was a discussion of calculation of energy difference between two successive rotational Raman levels. It was shown that what should be the energy of these Raman levels? The energy should be given by, what is the pointer? Yeah. So E for jth level, it was defined as BHC j into j plus 1. You know that it was also discussed, and now using delta j is equals to plus minus 2, which is the selection rule for Raman spectroscopy. Okay, for Raman spectroscopy, the selection rule is somewhat different from uh, IR or vibrational spectroscopy, and this will be also discussed why this is plus minus 2 in the later lectures. And for now on, for due to the for you just know this information, that is the selection rule for this transition is delta G is equals to plus minus 2. So if you just delta E, if you calculate, it will come like delta E, which is nothing but E of J plus 2 minus EJ, which is coming at 2 VHC into 2j plus 3. Okay. Now if we put different j values, you can get different energy levels. Okay. And then there was a discussion on the Stokes and anti-Stokes line in terms of wave number of the incident light source. Depending on the wave number or energy, any kind of thing of the incident light source, the Stokes and anti-Stokes line can be distinguished. Okay. And it was shown that this nu bar for in final should be nu bar incident plus minus how much was this 2b into 2j plus 3. This was also derived. Okay, so depending upon this value of b plus and plus minus, you know where should be the position of this new bar or what should be the positions of these Stokes and anti-Stokes lines. Okay, now the main advantage was there uh, for Raman spectroscopy is that the determination of the bond length of homonuclear diatomic molecules. Okay, so you know that in previous discussions when we are discussing about IR spectroscopy, we are unable to get the bond length corresponding to the homonuclear diatomic molecule. For heteronuclear diatomic molecule, you can get this bond length, but for homonuclear diatomic molecule, it was some restriction. Why? Why there was no problem? Because for rotational activity, you need permanent dipole moment, which is not the prerequisite condition for Raman spectroscopy. For Raman spectroscopy, your condition should be that your polarizability should change with the movement of the atoms. So, in case of diatomic homonuclear diatomic molecule like into O2, if you want to get the how what should be the bond length, you can clearly get it from the Raman spectroscopy. So, this is the advantage of this Raman spectroscopy over our other spectroscopy. In the next lecture, there was shown that the intensity of these rotational Raman spectral lines, they have a certain dependence on nuclear spin or centrosymmetric molecule, because it was shown that on the basis of nuclear spin for a centrosymmetric molecule, on the basis of nuclear spin, the rotational spectral lines will be different. Okay, suppose for oxygens like things for which I is equals to 0, in that case you can clearly see that the bands corresponds to z equals to 0, 2, 4, 6, that is not observed, which is written here over. Okay, and it was very well discussed by Professor Sanbakshi, and he has used the concept of nuclear spin wave function, which is based on these fermions or bosons, which kind of particles you were talking about. If you were talking about electrons, which is a fermion, okay, but if photon is a boson, okay. So whenever you are taking this molecule with this, you can consider it as fermion or boson, okay. And then if considering this nuclear spin, you can clearly say that which will be followed. That means which spectra will be there and what should be the wave function nature. And then using this concept, there was a discussion on ortho and para hydrogen. So this ortho and para is don't related with the organic chemistry, because this ortho and para hydrogen means they ortho hydrogen means the wave function of the nucleus spin when it is symmetric, and if it is anti-symmetric then it is called para hydrogen. So the two, when hydrogen molecule is formed by using two hydrogen atoms, these electrons will have spin, they can be arranged in the four order. Okay, so you have seen that the four different ways you can arrange that. So, and among these three are symmetric completely, and one is anti-symmetric. So one is anti-symmetric. Okay. So using this concept, you can get idea about ortho and para hydrogen. And also there was a small discussion on how the calculation of the number of symmetric modes and number of anti-symmetric modes in terms of nuclear spin. Okay, so it was shown for that symmetric modes is written as, what should be the equation? The equation should be written as 2i plus 1 for I nuclear spin. How much should be the symmetric mode? Symmetric mode will be given by this one, and if anti-symmetric mode is there, so anti-symmetric mode is given by only 2i plus 1 into I. Okay, so if you know I, that is this I is not moment of inertia, this is nuclear spin. Okay, so if you know this nuclear spin, you can clearly get idea about how many symmetric modes will be there and how many antisymmetric modes will be there. Okay, so this was the discussion on lecture number 40. So in the next lecture, in 14.1, there was a concept of polarizability. Okay, this is the change of the electric field, the electron density due to the electric field. What I have talked about in the very first lecture about on discussion of brief introduction of this first lecture, lecture number 37. Okay, so due to electric field, how this is changing the electron density. Okay, so this is termed as polarizability. And then it was showed that the dependence of the applied electric field on induced dipole moment in terms of polarizability. That was also there. Now, whenever there was a matrix representation, it was shown that alpha will have different kind of matrix representation. So a 3 cross 3 matrix will be there. This will be, sorry, this will be xy, xc. So alpha xy, y-axis, yx, alpha yy, alpha yz. Another should be alpha zx, alpha zy, alpha zc. Okay. So the polarizability was written in this form, and it was then converted to some other form, that is diagonalized, such that this your whole matrix become like this one: alpha x prime, alpha y prime. And you know what is the diagonal matrix, that is your off diagonal elements would be always 0. Okay. So this was discussed how to convert this into another coordinate, that is a 3 to 3 matrix. So symmetric matrix is converted to a diagonal matrix. And then the dimension of polarizability was also calculated, and it came as the L of L cube. That is, the dimensionality of volume is just same as the dimensionality of polarizability. And then the polarizability ellipsoid was formed. That is, polarizability in different directions will be different. So in the direction where polarizability is maximum, there will be more electron density. So there will be, you can see that polarizability will form a ellipsoid. Okay. So so that means ellipse, that the three sides are not equal. Okay. So this was all the discussions that was made about Raman spectroscopy, concept of polarizability, and how rotational Raman lines are divided into different rotational Raman lines are present. And also there was a discussion that for nuclear, for centrosymmetric molecules, how this is depend upon the nuclear spin. Okay. Now I'm going to solve some questions regarding these topics. So the first question lies in this one, that in a light matter interaction, incident light and scattered light has wavelengths alpha 1 and alpha 2. So you have to find the correct option, which, and you can see here there is the concept of Rayleigh scattering. Okay. So you have to tell me that under what should be the relation between lambda 1 and lambda 2 for Rayleigh scattering. So is there anyone? So I can, if I, is there anyone? So I can ask him or her. Okay, so I can see that no one is here. Okay, so the question you can, the answer you can find in the lecture number 37, that I have also said for Rayleigh scattering, the wavelength of the incident light will be always same as that of the wavelength of the scattered light will be same as that of the incident light. So if the scattered incident light has a wavelength associated with it as lambda 1, and the scattered light has a wavelength associated with it as lambda 2, so the relation will be lambda 1 always will be equals to lambda 2. So if lambda 1 is equals to lambda 2, then it is called Rayleigh scattering. Okay. So this is the concept behind Rayleigh scattering, that the incident light and the scattered light will have the same wavelength or same frequency or the same energy. Okay. This is the first question. So next question is, what on which factor Raman effect is related with? Okay. So Raman effect is related with the change in the dipole moment operator, change in polarizability, change in magnetic flux, or change in electric flux. So what should be the answer? So you can find this also in lecture number 38, where you have the answer is there. So in Raman effect, I have said, just like just like in rotational spectroscopy, the initial condition is that for rotational activity, your dipole moment, the molecule will be have a permanent dipole moment. In vibrational spectroscopy, there are some relaxation that dipole it need not to have a permanent dipole moment, but your dipole moment should change with time. Okay, and then also, and there in the Raman effect, it is shown that there is no cause of dipole moment, but your polarizability will always change with the displacement of the atoms. So for Raman spectroscopy, the concept is that your dq by dx, or dq by so condition is that your d alpha, if alpha I define it as polarizability, so d alpha by dx should not be equals to 0. Okay. So this condition must be satisfied to have a Raman effect. Okay. So molecules that doesn't support this condition, they will not show Raman. So the main Raman effect is related to the change in polarizability. So you have your answer. Your answer is over here. The change in polarizability should happen. Fine. If it was joined or not. No. Fine. Okay, so I have this. You got the answer that the change of polarizability is important for our Raman effect. Now, this is the next question that in a light matter interaction, incident light and scattered light has frequency nu1 and nu2 respectively. So you have to choose which one is the correct answer. Just like the question number one, where there was given the two wavelengths of light as the new lambda 1 and lambda 2, that is of one of the lambda 1 for incident radiation and lambda 2 for the scattered radiation. So what should be the relation? It was shown that the relation will be your lambda 1 should be equals to lambda 2. But for Stokes line here, there is discussion on Stokes line. So okay, so for Stokes line, what should be the condition? Okay, so just remember that in what I have told you, that for Stokes line, this is virtual state. So this is virtual state, this is final state, this is the initial state. Okay. So for a Stokes line, there will be a transition from here to here. So your transition will be from here to here. From this virtual state, it will come back to this final state. So you can see here the frequency or the associated with energy associated with the incident radiation. I write it at EI is greater than energy associated with scattered radiation or SC. I am writing it as SC. Okay. So I am writing IN and S is SC. That is incident and scattered. So you can see the incident radiation has more energy than the scattered radiation. Now, if I use both formula, this can write as nu IN greater than H nu SC. Right? Just I am writing E as a H nu. And next, so H will cancel from both the sides. So nu IN greater than nu SC. That means your incident light will have intensity. Your incident light will have a frequency which is higher than the emitted light. Okay, sorry, scattered light. So if in terms of this question, which is mentioning as incident light as nu1 and scattered light as nu2, I am writing the same symbol nu1 which will be greater than nu2. So this should be the condition for rotational. So sorry, this will be the condition for Stokes Raman scattering. Okay, so which of this will be correct? So you will get this answer in lecture number 37, where it is mentioned that when light interacts with matter, the scattered light may have frequency equals to or more or less than that of incident light. Three different phenomena can happen, that the scattered light have frequency which is higher than incident light or equal to incident light or lower than incident light. Okay. If it is equal, then it is called Rayleigh scattering. Okay. I mentioned here that if this is equal, then it is called Rayleigh scattering. But if this incident light has more frequency than the scattered light, then it is called Stokes line. And if it is has less, then it's called anti-Stokes line. Okay. So here you have asked about what should be the condition, what is the relation between nu1 and nu2 for Stokes line. So your answer is there, that your nu1 should be is equal greater than nu2 for Stokes line. So your answer is nu1 greater than nu2 corresponds to Stokes line. Okay. Okay, so I'm going to the next question. That is, in a light matter interaction, incident light and scattered light have frequency nu one and nu two. So you have to choose the correct option. The same questions. Okay. In the previous question, his question is just different. That in the previous question it was asked about your Stokes line, but now you have been asked about anti-Stokes line. The same thing. I'm just writing this drawing for anti-Stokes line. So this was so in case of anti-Stokes line, this is your initial state, and you will finish up here, and this is your virtual state. So your transition will happen from here, and you will come up to here. Okay, so you can see that is the E of incident light will be less than E of scattered light. Okay. Similarly, using this Bohr's condition, H nu incident less than H nu scattered. And next, if you consider it nu in less than nu scattered. Now you have no, in the last like the previous case, incident light is mentioned as nu 1 and scattered light is mentioned as nu 2. So your condition will be nu 1 less than nu 2. So this is the condition for anti-Stokes line. Okay. In the Stokes case, you have seen nu 1 should be greater than nu 2, but for case of anti-Stokes line, you have seen the condition should be nu 1 will be less than nu 2. So you can find this reaction in also lecture number 37, and the same explanation is given. I have given the same explanation. That is, that three phenomena could happen. If the incident light and scattered light has same frequency, then it is Rayleigh scattering. If it has more frequency, that means if the scattered light has more frequency than the incident light, then it will be these will be anti-Stokes line. And if the scattered light has less frequency than the incident light, so then it will be Stokes line. Okay. So your answer for anti-Stokes will be nu 1 less than nu 2. Okay. So your answer will be nu 1 less than nu 2. Fine. Okay. So for next question is a very simple question. That is, which of the following spectroscopy involves a virtual state? Okay, this is your question. Which of the following spectroscopy involves a virtual state? Raman, IR, UV, or rotational? You know, for rotational case, for UV and for IR, that is, this is related to which one? This is related to rotational spectroscopy is related to microwave radiation or microwave or rotational spectroscopy. This is vibrational. And UV and visible, you know, this is related to electronic. Okay. So in all these cases, you need some excited state. Okay. So some excited state will be there for these three cases. For IR, UV, and rotational spectroscopy, there will be always the presence of an excited state and another ground state. But in case of Raman, there is no such evidence for excited state. There should be a virtual state, okay, from which this is coming ground and giving you Stokes or anti-Stokes light. So the answer lies in lecture number 37 also, that in Raman spectroscopy, unlike other spectroscopy, no excited state is involved. Rather, a virtual state is present. So your answer should be Raman spectroscopy. Okay. Okay. So next question is, among the following molecules, both microwave and rotational Raman active molecule is CCl4, HBr, C2H4, and O2. So this is the question, that among which of the following is Raman as well as rotational Raman as well as rotational active. So first you need to know what two conditions should be filled up to be Raman active, and what conditions should be made to be a rotational activity. Okay. So to be a Raman active molecule, you need your condition should be your d mu to d mu. No, this will be E. Okay, so I am writing it in the lower portion. So this is the condition for Raman activity. And next it is rotational. So condition for this two you need to know. This condition is d alpha by dq, that is change in the polarizability should be non-zero with movement of the atom. Okay. Okay, so d alpha by dq should be equals to non-zero for Raman activity. Okay. But for rotational activity, your condition is nothing like that. Your condition should be, what is that? Yeah. So your condition for rotational activity will be permanent dipole moment. Your molecule should have permanent dipole moment. So these two conditions must be satisfied for the Raman activity as well as rotational activity alongside. Okay. So I'm going by one molecule. So I could make a table over here. So I'm writing a column, three column table. So I am writing in the left side as molecule. I am writing here as microwave activity. Another I am writing as Raman activity. So number one molecule is CCl4. So first molecule is CCl4. Okay. So you know CCl4. You know the structure. What should be the structure of CCl4? Okay. Right. This would be the structure of CCl4. So this one moment will act in this side, and this that means the group movement of these three chloride, and another moment will be this one. So this will cancel down. So you see it has mu is equals to 0. So what I've said that for molecule which has no permanent dipole moment, this will be rotationally inactive. So microwave activity, I am crossing it. Okay. So since it is not microwave active, so I am just crossing it and I am not going to the next one. Okay. Because you need to have something which has both activity. Okay. For HBr, next question. HBr will have permanent dipole moment. You know H and Br molecules are different. So H and Br, they are different. Okay. So it will have always a dipole moment. So it will be rotational. It will be rotationally active. Also, in case of, so if it is rotationally active, now I am going to the next column. Is it Raman active or not? Yes, it is also Raman active. So since it is a diatomic molecule, so its polarizability will change if you change the position of the bond. Okay, or you do if you change the position of the atoms. So it will also show Raman activity. So this is the molecule you are searching for, which has both the activity. Now you need to see if other molecules are also in this category or not. So for C2H4, I'm writing it over here. This is C2H4 is nothing but ethylene. So C double bond C, C, H, H. Okay. So E will also have mu is equals to 0. Its dipole moment is also 0. CH bonds will cancel out each other in totally symmetric configuration. So it will have a dipole moment of 0. So it will also be microwave inactive. So since it is microwave inactive, so I am not going to the Raman side. Now for oxygen, you know this will be Raman active. Okay. homonuclear diatomic molecule, they are non-active. But in the beginning, you know, for rotational activity, it will not show any rotational activity because the condition will it will not follow this condition, which is mu is equals to 0. Okay. So since mu is equals to 0, so your rotational activity will also not be there. So only one molecule will be there among this which has both rotational and Raman activity, that is HBr. So your answer will be HBr. What that? Okay. So moving to the next question, that which of the following lines are most intense? The three different phenomena I have talked about. One is Stokes line, one is Rayleigh scattered, another is anti-Stokes line. So this question is which one will have most intensity. Okay. So you can find the answer here also. You want to try? You want to try? Okay, fine. So so when light actually interacts with matter, I have what I have said to you, that the scattered light will have frequency which is equals to or less than that of the incident light. Fine. Okay. So whenever light is interacting with matter, the scattered light, that is the light that is scattered, it will have frequency which is equals to or more than or less or than that of the incident light. Okay, completely different or it may be same. But most of the photons have most of the photons scatters with frequency equals to that of the incident radiation. Okay, that means if you take whenever you are getting as a spectra, you will see if this is your incident line, you will see some peaks like that and like this. In this side also is this. Okay, so if you take intensity over here, intensity, and if you take energy or lambda, suppose anything in terms of lambda. Okay, so this is actually your Rayleigh scattering. These will have much more intensity than the other two. Okay, and among these Stokes and anti-Stokes at room temperature, Stokes scattering will have much more intensity than compared to anti-Stokes scattering. Why? Because I have told you the reason that Stokes scattering actually happen from the transition due to the virtual state, which happens from the ground vibrational level. Okay, and according to Boltzmann distribution at room temperature, ground vibrational level is mostly populated. Okay, so more Stokes and Stokes line will have much more intensity at room temperature compared to anti-Stokes line, but the two highest intensity will be due to this Rayleigh line. So the answer will be Rayleigh scattered lines. Okay. Okay. So I'm moving to the next question, which is that what should be the gap between the incident light and the first Stokes or anti-Stokes line? Okay. So what should be the gap? You have to find that. So you can find this answer also in lecture number 39, that the first or Stokes or anti-Stokes line appears at nu bar is equals to nu incident plus minus 6b. Why 6b? Because I have said you that your nu bar will be depend upon this nu bar excitation or incident plus or minus 2b into 2j plus 3. This is the formula. Okay. So you know If you put J equals to 0, that is first, so from here I can write that first Stokes or anti-Stokes line appears for J is equals to 0 to J equals to 2 transition, right? So accordingly, what I have said that for a Raman spectrum, there is a condition of um, selection rule. The selection rule states that delta J should be equals to plus minus 2. So first transition will be from J equals to 0 to J equal to 2 state. Okay. Now if you put J equals to 0, you can get that new bar should be equals to new incident plus minus 6p. Okay, mu bar incident plus minus 6p. So what should be the gap between this incident light and this scattered light? This gap will be 6b. Wherever it will plus minus plus 6b or minus 6b, the gap will be always 6b. So the correct answer is 6b. Okay. So from after that, the gaps will become 4b, 4b, 4b like that. But the first line, which is due to transition from z equals to 0 to z equals to 2, this will be at 6b from the incident radiation. Okay. So your correct answer, you got your answer. Answer is number 60. Fine. Now this is the next question. That given that unit of electric field is volts per meter, units of electric field is volt per meter. So you need to find what should the unit of polarizability. Okay, so you have to find that. So for that, you can find this answer in lecture number 41, where you have there was a derivation of the dimension of polarizability. So your equation actually tells that your mu induced, that is the induced dipole moment, which is proportional to E. Okay, and these, and if in more general term, you can write it as mu induced is equals to alpha E plus 1 by 2 beta E square plus dot 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 dot. Okay, but if E is not that much significant, I can neglect this term. Okay, so if my E, or that is the electric field which is involved, is not that much strong, so I can neglect the higher order terms. So I am left with only mu induced is equals to alpha into E. Okay, so alpha I can write it as mu induced divided by E. Now what should be your mu induced? The mu induced is the unit for mu induced is the dipole moment. And you know what is dipole moment? Charge into distance, right? So charge is written as coulomb, okay? Because here written as C is coulomb, and distance I can write it as meter. So I can write as charge as cm or coulomb meter. Not this is the chief minister, this is coulomb meter. Okay. So mu induced is, which is the dipole moment, is the multiplication of charge and distance. So if you can represent charge as c or coulomb here and distance as meter, so I can write as mu induced will have unit of coulomb meter. Okay. And the E is the electric field. Electric field has this unit V per m, volt per meter. Okay. So if I simplify it, this will be coulomb. Volt will be in the denominator. Okay. So it will come in the numerator and it will be -1, and meter will be there. Another meter will be here. So it will go up it will become meter square. The unit for B alpha will be coulomb volt inverse meter square, or in a more general term, coulomb meter square volt inverse. Okay, this should be the unit of alpha. So you have to find which should be your answer. I think is the first one is your answer. Coulomb meter square volt inverse. So this is your answer. That is the electric field. Electric field as unit of volt per meter. So your unit of polarizability will be calculated, and it will be given. It will be given as mu induced by electric field. And mu induced, mu induced is nothing but a dipole moment. It is the induced dipole moment. Okay. So if you, since it is a dipole moment, so it will have the form of charge into distance. The charge I can designate it at it as coulomb, and distance is designated as meter, so coulometer. And then electric field was designated as volt per meter. Okay, so I can make it coulomb meter square volt inverse. So this is your final answer for alpha. Okay. Okay. So I am moving to the next question. That is, the third and fourth lines in the rotational Raman spectra of CO are separated by 8 centimeter inverse. So what should be the rotational constant of in centimeter inverse? Okay. So you know, so you can find this answer also in lecture number 39, which discussed about rotational Raman spectroscopy. The energy difference between two successive rotational Raman levels is 4B. Okay, I have told you about that. So your energy for any rotational level J is given by B into J into J plus 1, or rather in term, rather for writing as B, I can write it as nu bar J. For J, any nu bar J is written as B J into J plus 1 semi inverse. Okay, so I'm calculating for differently for two different systems. Okay, so third line and fourth line. So it was observed that the delta nu bar, okay, for j is plus 2 to j to j plus 2 transition, that is transition from j to j plus 2, was given by the expression was 2b into 2j plus 3. And putting the values of j's, the first b value appeared as 6b. This is the, if this is the incident radiation, this is 6b, this is 10b. If you put this j values, you will get this answer. If j is equals to 0, this will be 3, 3 into 6, 3 into 2, this is 6b. J is equals to 1, this will be 5, 5 into 2, 10b. J is equals to 3, if you put j is equals to 3, j3 is equals to 6, 3, 9, 9 into 2, sorry. If j is equals to 1, so j is equals to 2, 2 to 4, 4, 3, 7, 7 to 14, 14b. Next, if you will get 18b. Okay, so the difference between two successive levels in the rotational Raman spectrum will be always 4b. So this is the 6b line due to the 6b line, which comes from the first line of Stokes or anti-Stokes, but from then it is always 4b gap. Okay, so you will have said that your third and fourth line is separated by 8 centimeter inverse. So